Hello everyone, my name is Kanaitet. In this video, I'm going to talk about derivative and optimization. In this video, I'm going to explain how optimization works and how it is used to solve the real-life problem. All right, first of all, what is optimization? Optimization derived from the word optimal, which means the best. Optimization in calculus is the process to find the maximum and the minimum values. We can use optimization to find the best and the most effective solution to the real-life problem. Before we find maximum and minimum, we need to understand how derivative works. Let's say we have a graph here, and the functions of the graph is x squared, and we have a line that is tangent to the graph, and let's say this point and x equal 1. So how can we find the slope of the line? It's simple. We can differentiate the functions. So the first derivative of a function is 2x. So how do we use this derivative to find the slope of the line? It's simple. We can just plug 1 into the equations. So will be 2. So this 2 means this is the slope of the line. So this means we can use this derivative to find the slope of any line that is tangent to the graph at any point. So how do we find maximum and minimum with this? Let's say on this graph, there's a maximum point and a minimum point. So the line that is tangent to the maximum point and the minimum point are horizontal line. They both are horizontal line, horizontal, horizontal, which also means the points, the slope of the lines are 0. So which also means f prime of 2.79773 is 0, and f prime of 4.53561 is also 0. We can conclude this by f prime of x equal to 0 has the critical point that is either maximum, minimum, or horizontal tangent. Right. So how can you use this in real life? We can use this in business. We can find the maximum revenue, or we can use it in manufacturing that can minimize the cost or the materials. And we can also use in transportation and logistics that we can maximize the space of the cargo. And we can also use in health and medicine that minimize the side effects. So we know how we use optimization in real life problem. So how do we solve that? It's simple. Here are some steps to help you solving the problem. First, you need to understand the problem. That's step 1. And then you can draw in like a picture, like diagrams or something to help you visualize the problem. And then step 3, you need to identify the variables and the constraints, like domain or restrictions. Restrictions. Step 4, you can translate the real life problem into mathematical functions. So you will have like the functions that you can work with, uh, stuff like this. Step 5, you can use derivative of the functions. And the step 6, you can use first derivative test, that is f prime of x equal to 0. As I have mentioned before, you can get maximum or minimum. And for the last step, you can use the x value that you'll get from step 6, and you can put it back to the original functions to get to check the answer. Here are the example questions. For the first question, a farmer wants to enclose a rectangular vegetable garden using 60 meters of fencing. The garden will be located against the side of a burn, so only 3 sides of fencing are needed. The burn wall serves as the fourth side. The farmer wants to maximize the growing area of 4 crops. So let's solve these questions together. First of all, the question asks the maximize area. So what are the other information that is given? Yes, we'll only use 60 meters of fencing, and we'll only use 3 sides. The rest will be the burn that we will not use this side, so we can ignore this. Let's say this side X and this one Y. We need to know the domain and restrictions. The question says we will only use 60 meters of fencing, so we can split 60 in half and we'll get 30. But we cannot use 30 because if we use 30, we don't have we don't have any values for this dimensions, this vertical dimension, so value cannot be 30 or either 0, which doesn't make any sense. So the domain of x will be between 0 and 30. So we have this fence 60 meters, so the perimeter of the fence will be 60, and this total perimeter of these 3 sides will be 60. So perimeter is 60. Perimeter is the sum of all the sides. So sum of all sides will be x plus y equals 60, which is 2x plus y equals 60. And we can set x to the other direction. So it's be equal 60 minus 2x. And we can find the area, maximum area. So where's the area of the rectangle? It's x times y. So we have y, these equations. So we have these equations for the y. We can substitute 60 minus 2x, and then we'll get 60x minus 2x squared. So how do we find the maximum area? First of all, we need to find the first derivative will be 60 minus 4x. And then we have to equal first derivative with 0, and we will get 60 minus 4x equals 0. So 4x equal 60, and the x will be 15. So we'll get 15 for the x. So let's say 15 is the side of this vertical side, and we have to find this y value. So we'll substitute 15 into y. It will be 2 15. So y is 30. We can also see the 15 is already in the domain, so this will be accepted. So the maximum area of the growing crops will be 15 times 30, and it's going to be 450 meters square. So let's go to the next problem. For the second questions, you are the product manager for the beverage company that manufactures cylindrical aluminum cans. Each can must have a volume of 355 centimeter squares. The material for the top and bottom costs $0.02 per centimeter square, while the material for the cuff side costs $0.01 per centimeter square. The manufacturing process requires that the radius must be at least 2 centimeter and at most 5 centimeter for production line compatibility. So let's solve these questions together. So the second question asks, we want is the manufacturing question. So we want the ideal size for the minimum cost. The minimum cost. So what are the informations given? Volume is gonna be 355 centimeter square. The can is a cylindrical shape, so it's gonna be a cylinder. And the price for the cost for the top and bottom is gonna be $0.02 per centimeter square. And then the cuff surface area for the it's gonna cost $0.01 per centimeter square. And the restrictions for this question is radius must be at least 2 and at most 5 centimeters. So we're good to go. First, we have volume, so we can find the height from the volume. So we can play around with the equations. We got the formula for the height. The volume is gonna be 355. Now we got an equation for the height. Right? And what we want to do is we want to find the cost respect to the R. So the cost gonna be there are two sides for the top and bottom, so they both are circle shape, so it's gonna be 2 pi r square, because the area of the circle is pi r square, and the top and bottom has two sides, so it's gonna be 2 pi r square. And we're gonna multiply with the cost, it's gonna be 0.02 plus. Okay, let's see the cuff side. If we unfold this cuff, we get this rectangular shape. What is the area for the rectangle? Is length, length times breadth, right? So the length, this length gonna be equal to the circumference of the circle. So it's gonna be 2 pi r, and breadth gonna be equal to h. So get 2 pi r h times 0.01. Now we can solve this. So we got 0.04 pi r squared plus 0.02 pi r, right? Pi r, and we can substitute this one into h. So we got 355 divided over pi r squared. Now we can cancel pi and this one of the r, and we'll get with this equations, 0.02 times 355 is gonna be 7.1 over r. Now we want now we want the minimum cost. To find minimum cost, we have to find the first derivative of the functions. So it's gonna be 0.08 by r minus 7.1 over r squared. Now, what do we have to do is we have to equal the first derivative to 0. So it's gonna be 0.08 pi r minus 7.1 over r squared is gonna equal 0. Now we can multiply r squared to the both sides. If we multiply r squared to the both sides, we got 0.08 pi r cubed minus 7.1 equals 0. Now we can find r. Now we can put 7.1 to the other side of the equations, and we can also put 0.08 pi to the other side. Now we get this. And to find r, we'll cube root this equation. So we get cube root of 7.1 over 0.08 pi. It's gonna be approximately equal to 3.0456 centimeters squared. So we'll see if the radius is in the domain. So 3.0456, let's say 3 is between 2 and 5, so we will accept this value. Now we get radius. Now we can find the height. So to find height, we can use this formula. So we'll write back this formula, and then we'll substitute r, this value, in the r. So we'll get q, q of 7.108 pi. I'm gonna use this one for the more accurate value. We'll get 12.18. It's going to approximately equal to 12.18 centimeter square. This one is not centimeter square. This one is only centimeter. Right. Let's go to question 3. The question 3 asks, as the production director for Mitsubishi Heavy Industries in 1941, you're overseeing the manufacturing of the new Kirobudai class aircraft carriers. Naval Command indicates that at the price of 60,000 yen per carrier, they will order 8 carriers for the upcoming war expansion. However, for every 2,000 yen increase in price, the Navy reduced their order by 1 carrier. So find the maximum revenue. So want to find the maximum revenue for this one. Maximum revenue. So we'll see the given information. So the given information. So the first thing is they said they will use 60,000 yen. If we use 60,000 yen, we will get 8 carriers sold. And if we increase for every 2,000 yen, for every 2,000 yen increase, we will sell let 1 carrier less. So how do we make it? How do we make this into a mathematical equation? So it's simple. We'll find the revenue of X. We'll find the price. So 60,000 plus this increase in 2,000. We'll set X for the annual value, and we'll get 8 and minus X because we'll so less 1 carrier less. Right. So let's calculate this one. 480,000 minus 60,000 X plus 16,000 X minus 2,000 X squared. 180,000 minus 60,000 minus 16,000 or 44,000 x minus 2,000 x squared. So to find the maximum revenue, we'll differentiate this equation. So we'll get negative 44,000 minus 4,000 x. And we'll have to equal the first derivative with equal to 0. And then we will get 44,000 negative 44,000 minus 4,000x is equal to 0. So negative 4,000 is going to equal to 44,000 and x equal to negative 11. So we'll use this x uh, to put it back to the original equations in here to find the maximum revenue. So if we find of negative 11, we'll get 722,000. So I want to find the original revenue. So to find original revenue, we'll calculate the sold price times the carrier sold. So original revenue will be 60,000 times 8. It's gonna be 480,000 yens. So we can clearly see that this new equations we can get we have like more revenue for this equation. So 722,000 is greater than 480,000. And we also want to see the new price. So we'll put this negative 11 into this price, sorry, in this price equation. So we'll get the new price. So the new price will be 60,000 minus 22,000. It's going to be 38,000. So if we decrease the price to 38,000 yens, this means we'll sold more carrier and will make more revenue from this equation, according to this equation. So that's how optimization works in real life situations. So we can use optimization to find maximum revenue or minimum cost for uh, various industry. It's not really, it's not that 100% accurate, but it's still usable, reliable to use this calculus optimization for the real life example. Thank you guys. Thank you for listening.